All right. Thanks, Angela. So yeah, hey everyone, my name is Dalitso. I'm a research software development engineer at Microsoft with Azure Data, and my group is the Gray Systems Lab and the Azure Data. So Gray Systems Lab is an applied research group in Azure Data. So we focus on kind of making research products more of a reality, and we do lots of research projects and publish papers and that sort of thing. And then, we also provide like advice to product teams, and they take, the work that we do and take it to productization. So today I'll be talking about Raven. So Raven is a project that looks at extending relational query performance on inference. It's a system that is a set of optimizations that can be used on your machine learning queries within your database systems or other type of related systems. So this talk today, I will first go over the motivation behind machine learning inference, what it is, and why we do it, and what are the best ways to do it. Then I'll talk about Raven and how we use Raven to optimize ML inference, and why we use Raven and why we created it, the types of problems we're trying to solve. Then I'll go over some experiments and results we've done with Raven and show some numbers and show the improvements it gives us. And at the end, I will do some demos. I have some pre-recorded demos, so I'll show that at the end. So let's talk a bit about machine learning inference to provide some motivation for the talk. So in general, when we talk about machine learning inference, we're talking about feeding data to your models to get some kind of prediction or some answers. So you're querying your model for some meaningful piece of information. Typically, this is a prediction. So for example, you want to predict how long somebody is going to stay in hospital based on their symptoms or based on data you have about patients and that sort of thing. But it can also be, you have an image and you want to see if there is a cat in it, that sort of thing. And typically in machine learning inference, there are many ways to do it, but typically your pipeline follows this sort of path. You have your data set, and then you apply some transformations onto your data set. Really, these transformations can be, of the ETL kind, so sorting, filtering. So if you want the results ordered in a certain way, if there's some portion of your data that you don't want to really inspect, or that your machine learning model that you're going to feed into the next step doesn't use, you can filter out those portions of data. Some of these transformations can also include sort of featurizing your data. So typically machine learning models take in data in as kind of numeric format, so usually floats and that sort of thing. So in many cases, some transformations you apply to your data are converting, let's say, strings to categorical format so that it's all numbers that your model can understand. Or if you have classes, how can you encode that into some maybe more numeric friendly format that your machine learning model can understand? And so in the inference pipeline, we're not looking at training the model. Throughout this talk, I assume your models are already trained. So you have this model that takes in data that has been transformed and featurized, and its job is to give you a prediction. And this is like the typical stages of the pipeline. And this is just an example to make it more concrete, and I'll try to use this writing example throughout this talk. So we have a hospital, and we're trying to predict, how long how long a patient is going to stay in hospital. So your data set would look like, something like this. You'll have the patient's age, weight, heart rate, blood type, maybe their symptoms, and basically the characteristics of that patient. Your next step to get this ready for your machine learning model, you would probably do some kind of grouping of the medical records. So typically, all your medical records won't be all in like one table or one file, that sort of thing. So you'd have to aggregate them, let's say, like by the name of the patient, so that each patient has one line where you have all their details. You'd also likely have to do some filtering, because it's very likely that a lot of the information in your database isn't exactly relevant to what this machine learning model needs to predict, and the number of days this patient is going to stay. So maybe there might be information like there might be a patient's social security number or something, insurance information, something that's not at all relevant. Then tokenization. So we'll have patients' various fields, age, weight, heart rate, blood type, but we need a way to get that to a more numeric friendly format that the machine learning model can understand. So you have your blood types, A, B, O, and that sort of thing. So maybe you can encode those into some numbers, say A is 1, B is 2, that sort of thing. So that's tokenization in general. I'm sure you've seen most of these steps before. So this is a typical machine learning inference pipeline. So ultimately, that data gets passed to the machine learning model. Machine learning model gives you a prediction on the number of days this patient will be expected to stay. To get this to work, there are many ways you can do it, but maybe one of the most basic forms of having inference, basic stack you can use for this is, you have your data set as like a CSV file or a bunch of files. And then for doing the transformation, tokenization, and filtering and sorting of your data, you'd use something like Pandas or Spark. Panda is good for in-memory data frames and has a whole tool in Python in which you can do these transformations. Spark is typically used for larger data sets that don't fit in memory. And then your models would live in some machine learning framework. Typically, the ones use a TensorFlow or PyTorch for some of the big models for neural networks, that sort of thing. There's also scikit-learn for more traditional machine learning models. But typically, I would say there's generally a small, compared to the kind of the scale of maybe other different classes of software engineering, when you look at machine learning frameworks, there's normally a set that people use predominantly. And then you get your results at the end of the day. But there's issues with that kind of basic stack. One is, it's fragmented. You have all these different parts. They're not connected. And for the example I just gave, a hospital system, obvious challenge with that is security. You can't keep medical records just in CSV files. That seems like very risky. Because there is information that, under restrictions has to be kept private. And so if you're taking that information out of CSV files, then pumping it into your Python pipeline and then into your model, there's several opportunities for that information to leak. And obviously with files, you have the issues of durability. Files may get deleted. How do you manage this? How do you keep backups of the files? And also when your data gets way too big, you can't keep keeping everything in files. So typically the solution for that is moving on to a database, but you still have the issue of security in that your data will have to leave your database and make its way to your Pandas or Spark scripts to do the pre-processing, then make its way to the model. So there's still security issues there. Another issue is performance. Again, this stems from the fact that you're moving this data into these different stages of the pipeline. And these, as we talked about, these different stages seem to have different frameworks. So, you have your pandas, which may be different from the framework that you're using to store your data, and then you have your machine learning framework, which is also different, maybe different from your pandas and Spark that you're using. So it's not very coherent, and this moving of data always presents a challenge when it comes to performance. So a more improved version of this stack is you fit all your data into a database. So database can be SQL or maybe a Spark-friendly format like Parquet. But if you have your data there, you can kind of skip the step of doing all your transformations and sorting outside of where your data lives. So in SQL, you can query your data, and the result of the query can be sort of directly piped to your models for inference. You can kind of do away with having to do too much processing in pandas or some intermediate stage between getting the data from your database to your models. Because in SQL, you can make queries like, order by to sort the data. You can also do the filtering and all that within the database. And similarly, in Spark and frameworks like Spark SQL, you can have a lot of your ETL stuff being done wherever your database or data lake is, and your data comes out, it's ready to go into your model. So that's a much better way of running this stack. But again, there's still that gap between where your models are and database. And so there's chances for security issues to arise and for performance to not be as good. So systems like Raven take that just a step further. We say, okay, in what we call in database model inference. So we take your models to live where your database is, and this has been, I'll say, it's been rapidly integrated into more database systems now. So you have your models, and your models are kind of just like stored where your database is. And you can use a single query to take your data from the tables, sort it, transform it, and pass it into the models. And the result of the query is the prediction that you want. So we're kind of putting everything together, and that helps. One helps improve performance. Your models are right next to your data. They don't have to leave the closed system. It helps improve security, less chances of leaking out sensitive information, because everything is now in this like one big database, and it's not fragmented. Everything is kind of working together. We can avoid having using too many different frameworks within the database. So everything is contained, and that is ultimately a better experience, leads to better performance when running queries and inference on your machine learning models. So an example of what that would look like and what we've implemented in Raven is, you have your query, so a typical SQL query, except we supply the predict keyword. So now here, if I want to get the predicted length of stay for patients older than 20 years, I can write a query like this. So I say select, predict, I give it the name of my model, I give it the features or columns that are in my database that this model takes in as input, and then I can do my filtering with the where clause. And if I wanted to do sorting, I can add an order by and all that. So everything is contained in this SQL query that I pass to my database, and it gives me the results of inference, and that's the prediction and everything all together. So the key ideas here are, one, we get this improved experience by having models live where our data is, because everything is together. But then Raven one of the areas of optimization we introduced with Raven is now exploiting the fact that we have our data and the models together. Can we use knowledge about how our data is being processed to improve the runtime performance of our models? So intuitively, we're saying, oh, we have this data, and because we know in the SQL query how this data is going to be transformed, we know from the SQL query what sort of filtering is going to be done on this data. We know from the SQL query if it's going to be ordered and that sort of thing. Is there any way we can use that to improve the inference part when this data is sent to the model? Can we use that knowledge of what this data looks like, what has been done to the data to improve how the model runs? And the answer is yes. Raven comes up with a few classes of optimization centered around these ideas. One is avoiding unnecessary computation. If we know how the data is being filtered, for example, we know sort of what parts of the data are being left out and not being passed to the model. Intuitively, we can use that information to make the model more nimble. We can do things like reduce the size of the model if we know we're not sending all the data to it. It's only using a portion of the data. And that generally leads to better performance. Another big idea behind Raven optimizations is picking the best runtime for each operation. So if we know what the data looks like, what transformations have been done to it, we can maybe come up with a better sense of where to run inference on this ML model. I'll talk a bit more about that, but generally there's different environments where machine learning models can excel based on different characteristics. So some are good on the GPU, some are good on the CPU, and things like that. And that leads to point 3, learning where we can place these transformations, what sort of hardware to run these transformations on, can also give us extra optimization. So if we know maybe the size of our data, and we know what type of models we have, and we know how that's linked to the query, we can kind of figure out what's the best place to run this query and run this model to get improved performance. So some of the ideas behind Raven. And so in Raven, we end up formulating these 5 rules. Really, the first 4 are the ones that are important. Rule number 5 isn't so much of a rule, as opposed to it's just kind of taking in what we're already given. But the first 4 are key to the key contributions of Raven. So we have these rules: predicate-based model pruning, model projection pushdown, and model to SQL translation and hardware transformations. I'll now go into explaining a little bit more about how these rules work. So the first stage of Raven is coming up with this unified intermediate representation. So again, I have a query here: show me patients who are pregnant and predicted to stay more than 7 days. And so we'll have a query where you select predict to give it the name of the model. And this model is responsible for letting us know the number of days, giving us a prediction number of days the patient stay, and we're using the patient data table. And in this case, we're filtering for any patients who are pregnant. I also noticed the model is an Onyx file. That's kind of the standard format we use in Raven. So basically, Onyx is a way in which any machine learning model can be sort of represented. It's a format for expressing machine learning models. It's universal, so you can represent your TensorFlow, your PyTorch models or scikit-learn models as Onyx models. So it covers everything, and that's why we use it. And so Raven's first step of constructing this unified IR is as follows. We have your regular SQL query. So you can consider sort of the previous query without the predict part is what would be like at the bottom of this graph. And on top is the machine learning model. And the key insight is that your machine learning model represented as in Onyx format can also be represented as a graph. So here, basically, machine learning models can be considered the graphs of linear and ML operators. And SQL expressions can also be considered as graphs of SQL operators. So your graph of your joins, your filters, and predicates. For example, in this case, the predicate is pregnant is equal to 1. So they are very similar in the sense of that they can all basically be represented as DAGs, acyclic graphs of transformations. And what Raven tries to do is we come up with this unified IR. So we put the graphs together. So you have this one big graph where your SQL operations come first, and that goes into your ML model, ML operations that are like kind of a subgraph of that graph. And the IR can be composed of your relational, linear, and ML operators, and also UDFs. So UDF stands for user-defined functions, I think. So in SQL, there is opportunity for more kind of complex SQL tasks where there is not an inbuilt way of doing it. A user can supply functions to do whatever they like with the data as it flows in the graph. So UDF is another key thing that can fit into the graph. And again, so I said before, we use Onyx. So Onyx comes with a standardized way of representing machine learning models and creating these graphs. So we don't have to worry too much about, having a graph representation for PyTorch, a graph representation for TensorFlow, and that sort of thing, because Onyx is kind of this unified language. So that helps. And once we have that big graph, the unified IR, we can begin to talk more about what happens to it to apply the Raven rules for optimizations on your inference. So rule number 1 is predicate-based model pruning. Again, you have another SQL expression. So here, I'm trying to call my model. My model is called m.onyx, and I'm giving it patient data. And this model predicts the risk of the patient having COVID, COVID risk of this patient. And so I'm trying to, with this query, I'm trying to see the COVID risk of patients who have asthma. In this case, or in this example, if you look at the picture on the right, my model M is a tree classifier. So it's a very simple tree model. And below that, I have my my SQL graph. So you can think of the graph on the right as kind of the unified IR for this expression. And if you look at bottom right, I can see the columns from my tables that are going up into this tree model. So we take these columns, we do some transformations. So for example, in my asthma column, I'm using one hot encoding to convert asthma to some numeric representation that goes into my model. Then I have a concat node on top of that concats all these like featureized columns into a feature vector that goes into my tree classifier. And my tree classifies simply a decision tree. And based on the features, we arrive on one of the leaves that tells us this patient is low risk or high risk. So to do predicate-based model pruning, the first step is we introduce the predicate. So in this case, predicate is we want to look at patients who have asthma. So predicate asthma is equal to 1. And then in this step 2 and step 3, we replace the asthma node with a constant. So we make asthma is equal to 1, a constant. And let me see if I can turn on my pointer. Yeah. So we replace asthma is equal to 1, the constant here, and we propagate that through the SQL graph all the way to the model. And what happens once we place 1 here is our one hot encoder gives us this encoding where F2 is equal to 1, F3 is equal to 0. And then we see that the concat node adds all my features together. So F0, 1, 2, 3, 4, and 5 forms a vector. And because F2 and F3 are 1 and 0 respectively, if we look at the previous graph, we see that when F3 is equal to 1, when F3 equal to 1 is false, that's the only case where we go into this branch. So when F3 is equal to 1, we always go into this branch. And so we end up pruning a lot of the right side of the tree because it doesn't satisfy the predicate that has been passed. And so by setting this constant, we see that we're always going to one side of the graph, and the right side of the graph gets pruned out. And so that's the first rule, predicate-based model pruning, basically looking at your predicate and how it affects the graph and removing the parts that won't be touched by the predicate. Then I'll go through route 2, which is model projection push down. And this route is kind of similar to the predicate-based model pruning, but you can kind of think of it as predicate-based model pruning in sort of reverse. So we have a tree classifier here. So continuing from the previous example, our tree classifier has been pruned. And so now we can see that this model doesn't use all the features, right? We had features 0 to 5, but we're only using 0, 4, and 5. So 2 and 3 can be dropped because our model will not even look at them. And so to do that, in our graph, we add feature extractor nodes. So in Onyx, there is feature extractor nodes that you can add to say, I want to select this feature, I don't want to select this feature. And so we're just working backwards from the model and pushing this feature selector, feature extractor nodes all the way down. And once we get to the bottom, we can prune out the inputs that are not selected by these feature extractors. So in this case, feature 2 and 3, and basically this whole branch isn't selected by the feature extractors, and so that gets pruned out. And so the benefit of that now is by having predicate based pruning, we have a smaller model, and by doing model projection push down, we have a smaller SQL expression, so we're moving less data, and so that's likely to give us performance improvements when we run inference on this model. Rule 3 is model to SQL translation. The key insight with this rule is that we see that some ML ops, especially like the linear kind that you find in decision trees, random forest, that sort of thing, and also like the kind of these predicate type ML ops. So we see them in trees where you say, oh, this is go down this path if this is true or this is false. Or that can be, a lot of it can be expressed as case statements in SQL. So for like simple tree models like this one, we can convert it entirely to a SQL expression here. Why would we want to do that? Well, that allows us to do away with having to switch to your ML framework to run your models. If this is a SQL expression, it can be added to your previous SQL expression, and you no longer have to switch to PyTorch or TensorFlow to run your machine learning model. Now you have one big SQL expression that you can just execute on your SQL engine. And you can also leverage whatever SQL optimizers on your SQL engine to improve this query. So basically, you have your whole expression as SQL. Your data doesn't leave kind of this doesn't leave this space of SQL to be transferred to something else, and so likely to see performance improvements. But just a note on this transformation, it's hard to do for big models. So if you have big decision trees or more complex models, neural networks, it's hard to see how this can be done. But in some cases where you have these relatively simple tree models or linear models, you can get away with expressing your model as a SQL expression. And rule 4 is hardware transformations. So we leverage a project called Hummingbird, which is another project in the GSL group. And this project looks at translating traditional ML models to neural networks. The reason why that is beneficial is neural networks, a lot has been done in the community to get them to run efficiently on GPUs and ASICs and more specialized hardware. And so by converting types of machine learning models to neural networks, you can get them to exploit all these hardware optimizations that have been made for neural networks. So for example, in this case, we can take in this tree classifier, pass it through Hummingbird, and turn it into a neural network that we can run with PyTorch on GPU. So that gives us extra performance by exploiting the optimizations that come with running things, neural networks on GPU. And in addition, I guess in other cases where we can convert these models to neural networks, we can still kind of take advantage of the SQL optimizers that are always on. So whenever we have a SQL graph and leave it in SQL, we always get these SQL optimizations for free from like Spark, Catalyst, or whatever SQL optimizers are existing there. So not so much an addition of Hummingbird, but just something that we get for free. And that's what I cover in Rule 5. Just all these classes of DB optimizations we get for free by having our models just living in the DB. So in implementation, we have implemented Raven as a Spark extension. So we extend Spark's Parser and Spark's Optimizer in Spark Catalyst. And this, by doing it this way, we allow everything to look very similar to regular Spark. It's just an extension that we've added on, and the user would barely notice the difference. And so what happens is when your query comes in, and you start your Spark session, we have a Raven session that is basically a subclass of Spark session. and your query goes into Raven's parser. Raven's parser is responsible for identifying the predict keyword and identifying what model and what sort of columns you want to pass into your model, what sort of transformations you want to do in your query. And to run the predict step, we use a Raven predict Python UDF. So this allows us to allows us to run the Onyx runtime in like a Python sub process that will take in your data, and in this Python sub process we get call Onyx to run inference on your data. And the benefit of doing it all in this Python sub process is that Python is well understood for machine learning. We can also take advantage of having it easy to run things on GPU or CPU, because this is all, very much a regular Python script that is doing machine learning. So taking your model, goes to this Python script, and it runs there. There is a bit of overhead in that, there's this context switch from calling Spark into switching into this Python UDF in Python. And largely Spark is written in Scala, so there is a bit of a switch, but the Spark team has worked very hard to make the overhead very minimal. And so Python UDFs run almost as good as kind of like native Scala UDFs. We didn't see too much of an issue here. And then in Spark's main optimizer engine, which is called Catalyst, we add a Raven rule, which is one of the post-hoc resolution rules. So if anybody has used Spark Catalyst, it's a bunch of rules in Spark that are executed on each query. So we have a Raven rule that we have there. And that Raven rule is responsible for calling the various optimizations I just talked about that are here. We implemented these optimizations in Python. So again, this Raven rule start is a Python sub process here, and that will run these various rules. The reason we did it that way is, one, it's easier to write these rules in Python, but also it allows us to kind of package Raven better and even to make it more extensible. So for example, if somebody wanted to implement Raven in a different environment outside of Apache Spark, by having our rules in this Python package, they could still easily call this Python package and get the optimization benefits. And so in code, this is what it looks like. Running Raven is very similar to Spark, except we add a few configs that you can set. So here I have config for the rules, so I can turn on predicate-based model pruning or projection pushdown. And then I can use Spark as I would typically. It's a very easy transition for users to get to play around with Raven. And if you don't want to use Raven's optimizations, we also have a config where I can say Raven.optimizer, set it to false. I need to turn off all the Raven optimizations. So I'll go to experiments and results. So we tested Raven in a bunch of different data sets. Here I have a hospital data set, and I tested it across a bunch of different decision trees. So where it says DT, that's decision tree, logistic regression models, and gradient boosting models. And you can see that in every case, Raven gives us strong performance improvements over using regular Spark ML or using scikit-learn models or just calling the Onyx runtime. See, like in decision trees with like depth 5, so you get up to a 44 times improvement over Spark ML by applying these Raven optimizations. One thing we saw across the board was generally the predicate-based model pruning and projection pushdown optimizations were generally safe to do anytime. We found that the ML to SQL optimization worked well for smaller decision tree models. And then we found that for more complex tree models, more complex linear models, doing the machine learning to neural network transformation worked best for those models and gave us strongest gains there. Oops, this isn't showing right. I don't know why this graph isn't showing right. But in this graph, we are looking at, sorry. So if this could show correctly, what it's showing is that for different tree models, so we look at gradient boosting tree models of different complexities, we see that having the models run on GPU gives us better performance the more complex the model is. So up to 8 times performance improvement for a big tree model with 500 estimators can be seen from running it on GPU with Raven. There is also some advantage of running it, models on CPU with Raven, but we see biggest gains on complex models being run on GPU. And for simpler models, there wasn't too much of improvement running CPU and regular Spark. Then we also kind of looked more deeply into the effects of each optimization. So we looked at how projection push down improves performance across different sizes. And as expected, the bigger your data set grows, these improvements you make by pruning some inputs on your graph give us big benefits as your data increases in size. And ML to SQL, we saw like massive improvements by converting some models to SQL. These were mostly like tree models and linear models that were not too complex. You can convert them all to SQL and do away with kind of your ML runtime, run this a big SQL statement. And we also saw big improvements by converting models to neural networks and running on GPU. And these improvements became more impactful as your data grew in size. Then finally, one thing we also tried to do was like analyze how Raven would do in the wild. So we downloaded 800 plus models from OpenML, so random models of the internet. We converted them to Onyx. So some models couldn't be converted to Onyx just due to like versioning differences and that sort of thing. But we did our best. So we got about 400. Then over those 400, about 287 were kind of like meaningful standard ML models that we could really analyze and work with. Some had some Onyx runtime errors, and so that got reduced down to 240 valid models that we ran with Raven. And then we tried to also analyze the distribution on these models. We found that, interestingly, a good number of them had unused features, so they presented many opportunities for pruning with projection push down and predicate push down. And even though there was a huge kind of spread in the number of features the models had, we're surprised to see that many of them had a good percent of unused features. There are also many tree-based models. And the average tree depth. So this is kind of log scale. And there's some variance in the tree depth and number of trees within the models. But as we explained earlier, like Raven, applying the GPU conversion worked for these like deeper and more complex tree models. And then for simpler models, that we found that the ML to SQL conversion worked best for those models. So it's showing that there's a wide variety of models out there, and that presents lots of room for optimizations for Raven. Yeah, so I think I'm done with the majority of the talk. I'll now show a demo just to see how Raven works, and we'll see like the speed up Raven gives. So I hope this plays. Looks like that one didn't play.
I can see your Jupyter notebook now.
Okay, great. Second. I can just share my screen directly. I was trying to use Teams presentation feature. So
Oh, okay.
let me stop this. Share my screen. Oh, can you hear the audio from my computer?
No, we cannot.
Oh, let me see if I can fix that real quick. Okay.
Is Raven Spark running inside a modified HDN site cluster?
Yes, there it is.
Okay.
First, we'll show the data that we'll be working with. This hospital data set has 24 columns, 9 numeric features, and 15 categorical features. The data set has around 302,000 rows. Here's the Onyx model that we'll be working with. First, on the left are the 9 numeric features. Notice that 0 in the dimension of the inputs indicates the batch dimension. In our implementation, we are using batches of 10K inputs. The 9 numeric features are preprocessed by a standard scalar operator. And then on the right are the 15 categorical features. The 15 categorical features are preprocessed by one hot encoder. These features are input into a tree ensemble classifier. Going back to our notebook, we'll start the Raven session, and for the first run, we'll show the query without any of our Raven optimizations. Notice that we have introduced a new predict operator in Spark that allows us to execute Onyx models by invoking Onyx runtime. It takes as input the model and the data that we'll be using for scoring. For all of our sessions, we use Arrow and batch inference to speed up scoring. Now, with a little bit of video speed up for the sake of time, we can see that this runs in 11 seconds without any optimizations. And here you can see the output. Taking a look at our query plan in the Spark history server, you can see how our model is invoked by passing it the 24 features. Now we will show you the model projection pushdown Raven optimization in practice, using the same model, data, and query as before. With a bit of video speed up, you see that this query runs in 8 seconds, which is 3 seconds faster than in the version without optimizations. And here we show the data. If we go to the Spark history server and look at the query plan, we can see that here Raven is using the optimized model, and that we are only using 16 features instead of all 24. Taking a look at the optimized model, you can see how there are only 7 categorical features used instead of 15, as before. Here we are with enabling the ML to SQL optimization on top of the model projection pushdown. We don't need video speedup now, as this runs in about 1 second. Again, we show the data to verify it's there. Now back in the Spark history server, we see very little except the SQL query, which will be run entirely in Spark without any need for Onyx runtime.
Okay, that was quick demo of Raven. And then this is one that is a bit more in depth.
So the audio on that is kind of muffled.
Yeah, let me see if I can improve that. Is it
And then just as an aside, we've got 9 minutes until the bottom of the hour.
Okay, I think this is 3 more minutes. Is the audio better now?
It's about the same. Yeah, it's pretty muffled and hard to understand.
Oh, okay. Yeah, anyway, I can skip this demo. It wasn't that important. The first one was more important. This basically with this second demo, just wanted to show a bit more like step by step across more different models, but the results are basically the same. What we saw was that we get tremendous like performance improvements in models by running them with Raven. And another thing we want to show with this demo is that the user has to do very little, almost nothing at all to set Raven. They just have to say, oh, import Raven and Raven optimizer is equal to true, and that's it. And your program runs with the Raven optimizations. Yeah, I think that was it for my talk. I'll now leave time for questions.
Great. So I don't see any questions in the chat, but I do have a question. So because we couldn't see that second demo, is that available once we get a slide deck from you?
Yeah, it should be available in the slide deck. Yep.
Oh, perfect. Thank you.